Hello everyone. Today's live session 5 for the course Optical Fiber Sensor. I am Ankur Khapre, teaching assistant, and today we'll go through the week 5 content in briefly. After that we'll go for the question and answer sessions. So first we'll just start from the optical sensors, which are based on the amplitude modulated optical sensor, and you can see in the first picture over here that the gas is absorbing the light. Then here you can see that oximeter, it's shown in the sketch form, where we are putting our finger and using the oximeter to get information about the oxygen level in our blood, as well as it can be used for the heart rate as well, heart rate measurement. And here is a light source shown for the amplitude modulation, where the intensity can go up and down. So there are two kinds of models. One is digital or binary model, another is analog model. In digital model, what happens is you are having a kind of door where the light is coming inside, and suddenly if you are closing the door, at the time exactly the uh, input light will stop. Similarly, as shown in voltage versus time plot, that how the voltage, the photodetector is getting the voltage because of the conversion, photovoltaic conversion. Then from here suddenly it is decreasing to the low level, where because of the door is closed. Similarly, but not the same way, analog model also carries the information where the particles will either scatter or absorb the uh, light, and because of that, using the Beer-Lambert law, which is I is equal to I naught e to the power minus alpha z, so based on that the intensity will decrease exponentially. It's shown in this particular plot, versus voltage versus time. So you can understand that the binary is like a immediately shutting down to the low level or high level without any delay, but in this transition will happen exponentially. So why is it so? Because the absorption spectroscopy, where the actually the molecule gets absorb the light and goes to the excited state, or to the higher electronic state, and because of that we'll get the responsive absorption wavelength, resonant wavelength. But along with that, there will be one more thing it is happening, which is Doppler and collision broadening. This is happening because of the Doppler effect. The broadening is happening because of the Doppler effect. And to detect a specific target like pollutant, explosive, and the source must match the target's unique resonant transition cross section, which is sigma lambda. Moving towards the next thing, which is the differential absorption. Why it is important to, because to solve the unknown loss, why it is happening and what is happening. So to understand the unknown loss, we need to have two things, which is path A and path B. In path A, there will be a resonant condition. So lambda, which is resonating, it will be transmitted to the gaseous cloud, and in the second way, their path B, where the lambda with is non-resonant is also propagated. So it can, you can see that the unknown loss can be easily solved based on this equation, which is intensity of the lambda resonant and divide by intensity of the lambda non-resonant. So by taking the ratio of the resonant and versus non-resonant measurement, background losses cut out, isolating the target gas. second. Yeah, so moving towards the next thing, this is for the unknown loss, and moving towards the next thing, which is the, as we know that the SNR, to increase the SNR we need to increase the accumulation. However, um, the noise density, which is um, um 1 by f flicker noise, will decrease with will uh, decrease with increasing the frequency. So if you increase the number of uh, if you increase the frequency, then the precision will go down and down. Okay, so 1 by f uh, flicker noise is also plays a prominent role in the precision, where the DC measurement, like trying to hear a whisper in a crowded room, electronic component flicker dominates low frequencies. And you can see here that the frequency is already having the thermal short noise floor, but this noise density, which is because of the 1 by f noise, is dominating on the precision. That's why the lock-in detection is important, and where the lock-in amplifier increases the SNR value up to 50,000 counts. And you can see here how it is happening. The static measurement drawn here, it's because of the pink region is because of the noisy, and white region is having the white region where the signal can be seen properly because of the high SNR value. Okay, so this is how the lock-in detection improves the signal SNR, signal to noise ratio. Another thing is like, to application wise, it is very important for the oximeter, pulse oximeter, where the physiology in that it can be used, it is being used as a uh, one of the main tool for to measure the oxygenated HbO2 hemoglobin. And you can see here in the absorption spectrum that the deoxygenated hemoglobin, which contains porphyrin and iron, has the absorption in the red region, which is around 650 something. But while it's oxygenated, then the absorption region shifts to the 940 approximately something. And because of that, it can be useful to understand that how much oxygenated concentration is there in hemoglobin. So we can measure the oxygenated to deoxygenated hemoglobin using two distinct wavelengths. Just we need two wavelengths to understand whether the absorption is because of the deoxygenated, and another should be for the oxygenated hemoglobin. For that, the AC component 1 to 2% of signal carries the oxygen data. You can understand here. Other things are because of the DC component, which is tissue, bone, venom, venous blood, veins of bloods. Okay, so this just only 1 to 2% of the signal carries the oxygen data. And for the behind engineering of this, there is, I just discussed about this one here, that there will be requirement of two distinct wavelengths. Here it's mentioned as red LED pulses and IR LED pulses. With the between the those pulses there will be a constant gap. So what it does is, as the Professor Kumar's insight, by applying a natural logarithm, Professor Kumar has begun one lecture in the week 5. By applying a natural logarithm, we linearize the Beer-Lemma law. The result depends on the blood volume changes independent of skin color or absolute intensity. So anyhow, the because of the tissue and so many things, skin color also can be interfere the blood oxygen calculation or measurement. But it's a despite of that being a different skin color or having the tissue density or something, it can actually measure precision, with a very high precision. So for that, this is the equation: S lambda is equal to ln V lambda minus ln V lambda at t0. So initially how much the voltage, and after that how much the voltage is, can be easily understand with that oxygen concentration. Now moving towards the OTT. For that OTDR, optical time domain refractometry, the light pulses will be sent with a few with a fixed time of flight. So where there will be fixed frequency, so the time of flight will be calculated based on the detection time, and time of flight is del t, and it's not actually del t, because this should be 2 times, because once it is going, the laser pulse is hitting to the sample and the Rayleigh scattering is moving back to the detector, and this is called the time of flight. The concept is we rely on the Rayleigh scattering, the fraction of light that bounce back. So the distance will be c into del t by 2, and 2 is because of the round trip. Reading the trace, reflection connector, and the event splice or ground cloud. So you can see here the log power and distance plot has been given, where the reflection and the event of glass, because of the gas cloud, can be analyzed, or based on the trace reading it can be analyzed. The slope reveals the loss coefficient. A sudden drop indicates the specific absorption event, such as gas leak or fiber fault. So that's what we need to take care of the trace reading, not the reflection, or it's like a connector problem, because of the connector problem. Similarly, there will be a trade-off in the design. So Maker's equation, there will be a resolution which can be achieved using the Vg into tau p divided by 2. So what is happening here is, if you have the long pulses, it will be required high energy, which is long pulse high energy, and maximum range or resolution will be low. Resolution will be low, range will be high, but resolution will be low. But while if you are using the short pulse, which can contain low energy at the short pulse range. Short pulse laser pulse or LED pulse will be having the short range, but the precision will be very high. So that's what need to do the trade-off in the maker's equation, and it should be in the middle of that. Either it should not be a low resolution or it should not be a short range. So we need to play into the equation and need to maintain the both the parameters in one output or one device. For that, 1 microsecond pulse gives 100-meter resolution, a 10 nanosecond pulse gives 1 meter resolution but requires significantly more averaging. So that's why we need to trade off with the both the parts. Moving towards the industrial application, where the nitric oxide monitoring, where the industrial flue gas will be having cell length around 0.5 meter and frequency 10 hertz. Selected source is DFB laser, distributed feedback laser, and narrow line width less than 6 gigahertz. And the design logic, silicon detectors are blind at 1100 nanometer. So that's why we need to use the indium gallium arsenide. And distributed feedback lasers provides a narrow line width required for specific gas peak. So that's why the industrial application we need to optimize the condition for the specific application. Moving towards the power and gain budgeting, where the launch power, it is approximately 1 milliwatt. If you are giving because of the external loss, there will be scattering or window loss, so there will be almost 0.1 milliwatt. It will go to the detection side, and where 10% signal modulation will happen, and based on that the TIA gain, after TIA gain with 14.3 kilo ohm, it will achieve some kind of readable signal. So goal is to convert 70 microampere current to fill the 0 to 1 volt ADC range. Minimum detectable limit 1 by F noise, low frequency drift 15%, and short noise is approximately 55%, and thermal noise is approximately 30%. So total it will be 100% noise. So we need to maintain the minimum detectable limit. So how much we can detect? So noise current divided by responsivity into path length into power will give us the minimum detectable limit. So if you have noise current very high, then detectable limit will be higher, minimum detection limit will be higher. So that's why we need to play with the power and path length. We need to optimize also the responsivity. Optimization strategy: to detect part per billion, we must maximize power and minimize noise equivalent power using lock-in technique. Now we have discussed about the amplitude modulation of the light and some specific application. So here are the future of the amplitude modulation, where elevator door can be seen that how it is detecting our hand or our gesture to open or keep it open for a while entering into the elevator. Next is pulse oximeter, where the oxygen oxygenated hemoglobin can be easily calculated without any in vitro or lab testing, without any lab testing. Then OTDR can be calculated. Then differential absorption we have discussed. Then wavelength modulation spectroscopy, where the frequency will be doubled, like nonlinear optics. So next gen tech contains the wavelength modulation spectroscopy. Modulating the wavelength and detecting at 2f eliminates background slope entirely. Second thing is closing thought, the perfect sensor balance physics, electronics. Physics means absorption, electronics means noise, and mathematics means signal processing. Moving towards the question answer session. Yeah. So let's take a 5 minutes break, and after that we'll start for the question answer session. Okay, so moving towards the question answer session, we'll discuss about the first question where um, um, we are going to the basic questions, uh, based memory based questions. So first question is, in the context of optical sensors, why is an amplitude intensity modulated sensor considered easier to build than polarization or phase modulated sensors? So option A is, intensity sensor do not require an optical source to function. B is, amplitude modulation is inherently immune to external noise source. C is, the optical receiver can directly detect changes in power without a demodulator. And D is, phase changes are naturally converted to voltage by standard photodiodes. So uh, what could be the answer here? The answer, correct answer, we need to find out. Intensity sensor do not require optical source as a function. That is not correct. We required it. Second thing, amplitude modulation is inherently immune to external noise source. It's not like that. Each and every modulation has the external noise uh, source. Then optical receiver can directly detect change in power without a demodulator. Yeah, so uh, without changing the power, without demodulating, we can directly detect change in power. So we don't need to demodulate it. So that's why the amplitude modulated sensors are considered easier. The last option is, phase changes are naturally converted to voltage by standard photodiode. Yes, correct, or it's not. Phase changes are naturally converted to voltage by standard photodiode. No, we need something to detect first phase, which phase the light is. Okay, moving towards the next question. According to Beer-Lambert law, the transmitted intensity I lambda through a gas shell is given by I lambda is equal to I naught e to the power minus sigma nl. What does the parameter sigma represents? A number density of the gas species per unit volume, the physical length of the interaction path, the transition cross section of the species, the external loss fraction due to scattering. First option, the number density of the gases per unit volume, that is n, that is not this sigma. The physical length of the interaction path, that is L, it's not. The transition cross section of the species, that's the correct answer. This is the transition cross section of the species. Then there will be another, the external loss fraction due to the scattering. Now this is not external loss fraction. Moving towards the next question, why is the mid infrared region preferred for high sensitivity trace gas detection? The first option is, silicon photodiode are most sensitive at mid IR wavelengths. Second is, mid IR lasers have much broader line width than visible lasers. Third one is, relay scattering increases exponentially at longer mid IR wavelength. And fourth is, the absorption cross section sigma is significantly higher in the mid IR than the visible region. So silicon photodiodes are the most sensitive at the mid IR wavelength. That is not correct. It's having in a visible range and near IR range most detection or sensitivity. Indium gallium arsenide has the detection range in the mid IR. Mid IR lasers have much broader line width than visible laser. It's not correct. It should be having it will be sharper like a visible laser only. Rayleigh scattering increases exponentially at longer mid IR wavelength. So here this is also not correct. The correct answer is the absorption cross section sigma is significantly higher in the mid IR than in the visible range. So that's the reason we need to take the mid IR for high sensitivity gas trace gas detection. Okay, so mid IR is the best for this kind of thing. Okay. Moving towards the next question, which is in differential absorption spectroscopy, why is the second measurement taken as at a non-resonant wavelength lambda nr to account for and cancel out unknown external losses unrelated to absorption? B. To double the effective interaction length of the gas shell. C. To induce Doppler broadening for better signal resolution. D. To ensure laser reaches its detection, its threshold current more effectively. So the first option here is to account for and cancel out external unknown external losses unrelated to absorption. That is the correct answer. We have discussed about the intensity of the lambda r resonant divided by intensity of the lambda nr. Okay, which can be understand easily. Moving towards the next question, what is the primary reason for employing lock-in detection at frequencies like 10 kHz in amplitude modulated sensor? First option is to eliminate the need for an analog to digital converter ADC. B. To avoid the high noise density of 1 by f flicker noise found at low frequencies. 2. Increase the spatial resolution of the remote sensing probe. D. To ensure the semiconductor laser operates in a multi-mode region. So here the option A says to eliminate the need for an analog to digital converter. That is not correct. It nothing is related to ADC. Second, to avoid high noise density of 1 by f flicker noise found at low frequency. That is correct. That is why we are using the primary reason to use lock-in detection at frequency like 10 kHz in amplitude modulated sensors. Third option is to increase the spatial resolution of the remote sensing probe. That is not correct. To ensure the semiconductor laser operates in a multi-mode region. That is also not correct. In pulse oximetry, which two wavelengths are typically used to distinguish between oxygenated hemoglobin HbO2 and deoxygenated hemoglobin? So there we discussed already the red and infrared we use to distinguish between oxygenated and deoxygenated. So this is not correct. Violet and red we are using because the porphyrin, oxygenated porphyrin absorbs near to 940 and deoxygenated hemoglobin absorbs near to the which is porphyrin containing iron, which absorbs near to the 680 nanometer red, 680 nanometer, which is almost near to red. So this is the correct answer. This 1350 and 1310 and 1550 is not correct. 500 and 600 also not correct. So this is how it works. Moving towards the next question, which is in optical time domain reflectometry OTDR, what is the trade-off when increasing the pulse width tau p? Increasing tau p increases Rayleigh scattering but decreases the speed of light in a fiber. Moving towards the option B, increasing tau p improves spatial resolution while reducing the dynamic range. Option C, increasing tau p improves the backscatter power but degrades the spatial resolution. Increasing tau p requires no transimpedance gain in the receiver. So first option is not correct, second option also not correct, third option is the correct, because the pulse width improves the backscatter power but degrades the spatial resolution. If you go for longer region, here we can understand how we, yeah, so resolution will be low. Okay, moving towards the last option, increasing power, low transimpedance gain to in the receiver, that is nothing related to this particular property. Moving towards the next question, if an OTDR performs n is equal to 2 to the power 16 averages, what is expected signal to noise ratio improvement SNR SNIR in decibel? Just a second. Okay, so the correct answer here uh, will be, we need to calculate. So for an OTDR system performs, which is n is equal to 2 to the power 16, and expected SNIR in decibel we can calculate using SNIR is equal to 1.5 can write here. SNIR is equal to 1.5 log 2 n, and if we keep n value here, which is 2 to the power 16, becomes 1.5 into 16, approximately 16 uh, 24 decibel. So the correct answer will be 24 decibel, option 3. Moving towards the next question, why is an distributed feedback laser specifically chosen for high resolution gas spectroscopy for nitric oxide? So option A says it has an internal loss coefficient of 0 due to periodic grating. Second is it provides a narrow line width much smaller than the spectral width of absorption transition. Third is it naturally oscillates in multiple longitudinal modes to cover more ground. And D, it has the only laser type capable of emitting at 1100 nanometer. So option 1 is not correct here. It doesn't have any internal loss coefficient, which is 0 due to periodic grating. It also option B is the correct here because it provides a narrow line width which is smaller than the spectral width of absorption region transition. That's why we need to use the DAP laser. Option C is also not correct here, and option D, which says the laser type capable of emitting at 1100, which is also not correct. Moving towards the last question, in wavelength modulation spectroscopy (WMS), why is detection often performed at the second harmonic frequency? So the first option is standard laser can only be modulated at even harmonics. B says option B, it results in a zero background measurement where the signal is proportional to the curvature of the absorption line. Option C says it allows the use of slower, cheaper photodiode with higher capacitance. And the last option is the second harmonic generation frequency has double the 1 by f noise of the fundamental. So first option is not correct here. Even harmonics it's not related with this, because second harmonic can be having the some frequency generation and different frequency generation also, differential frequency generation also. Then option B, that is also not correct. So option C also not correct. So the correct answer is option D. Option C says it allows the use of slower, cheaper photodiode with higher capacitance. It's not like that. The option D, the second harmonic frequency has double the 1 by f noise of the fundamental. So that is important for that. Okay, so other than that we'll discuss in the next class next week. So see you again. Bye bye.